3i Atlas has just increased its brightness and no one expected this. That sentence became the unexpected alert that began circulating among astronomers from different countries when the first measurements revealed a change that did not appear in any previous projections. The magnitude observed in the last few hours simply did not match earlier records, and that immediately drew attention because such a marked increase does not usually happen without some measurable physical activity behind it, something real and tangible. It was not a rumor or an exaggerated interpretation. It was a fact confirmed by separate instruments operated by teams that were not even coordinating with one another. The moment those independent detections overlapped, it became clear that we were facing a behavior that needed to be understood calmly, rigorously, and without jumping to hasty conclusions. While the values continued to update, the scientific community began to review every observation, searching for technical inconsistencies, calibration errors, or any external factor that might explain the difference. But the checks all agreed. The light curve showed a sudden jump, a change that had not appeared so strongly in previous records. And although the phenomenon was not linked to any strange or speculative event, it did place 3i Atlas once again under intense scrutiny, because a luminosity increase in an interstellar object always raises questions about its surface activity, its interaction with solar radiation, and the amount of material it is releasing. At that point, new comparisons with earlier days emerged, revealing that the rate of increase had been faster than expected for that stage of its trajectory inside the solar system. None of this implied dramatic conclusions, but it did require an adjustment in how the data were being interpreted. And it is precisely that need to understand what had changed that makes this moment so relevant. Before going into the technical details of the recent behavior of 3i Atlas, I would like to ask you to support this work by giving it a like and commenting where you are watching from. That helps us enormously so this content reaches more people who closely follow what is happening with this object that is still inside the solar system and continues to provide real, verifiable, and scientific measurements. The recent history of 3i Atlas has been followed by numerous ground-based and space observatories, not because of speculation, but because of the importance of understanding how objects that do not originally belong to our system behave. Every brightness change, every variation in its coma, every update in trajectory or activity is valuable data that allows specialists to compare models, review sublimation mechanisms, and better understand the dynamics of bodies arriving from distant interstellar regions. And when a sudden brightness increase is recorded consistently, it becomes a priority topic of study. What we are seeing now is a phase in which instruments continue to detect activity that can be explained by known physical processes without the need for assumptions. Brightness is one of the most direct signals for evaluating how much material is being released and how solar radiation is interacting with its surface. Therefore, every new update becomes as important as the previous one, and every observed detail helps build a more complete picture of the phenomenon. In the following sections we will examine exactly how that brightness increase was detected, what data confirm it, what physical mechanisms may be involved, and how the scientific community is interpreting each signal observed so far. When the first records began to show that the brightness of 3i Atlas had changed with unusual intensity, the teams monitoring non-periodic trajectory objects immediately started a thorough review of the available values. Not because an extraordinary event was expected, but because such a marked increase recorded over a relatively short interval demanded careful verification. The initial detection came from photometric measurements taken during a continuous observation period in which several telescopes were routinely collecting data on its behavior. Those measurements, taken in different optical filters, showed a consistency that caught attention even before the values were compared with previous days. The apparent magnitude of the object had changed more than projected, and that could only be confirmed with further independent data. The first reaction of the researchers was to review the instrumental record. Photometry can be extremely sensitive to external factors such as atmospheric turbulence, light pollution, inaccurate calibration, or thermal fluctuations in detectors. Therefore, before interpreting any change, it became necessary to rule out any interference. The images were evaluated one by one, checking sky stability, reference stars, pattern within the same field, and light curve consistency, yet even under prolonged scrutiny the data continued to indicate the same behavior. The object was brighter than in the previous temporal sequence. There was no obvious technical anomaly that could justify that jump. With that initial confirmation, the next step was to compare the values with data recorded by other observatories that had also maintained regular follow-up. In scientific terms, correlating independent readings is a fundamental way to validate any photometric measurement, and in this case the values from different instruments agreed within the expected margin, even though each telescope had its own range and resolution. What mattered was that the trend was the same. The brightness had intensified in a real and verifiable way. From that point onward, attention focused on understanding which part of the object's physical behavior might be related to that variation. Brightness increases in active bodies are usually associated with the release of particles, gases, or fragments that reflect more sunlight. It is not an assumption but a known and repeatedly measured mechanism in comets and objects with observed surface activity. When fine particles escape from the surface, the coma becomes denser and wider, which increases apparent luminosity. It is a documented physical process that requires no speculative explanations. Still, each object has its own particular dynamics, and 3I Atlas is no exception. To determine whether that mechanism was involved, it was enough to evaluate the light distribution around the nucleus using aperture photometry. If total brightness increased proportionally in larger apertures, it was a sign of material expansion. And that was exactly what several measurements showed, a more extended distribution than in previous days, indicating that the coma was scattering more sunlight. This did not mean a sudden change in its internal structure or a particularly rare event, but it did confirm that surface activity was recording measurable variations. Another point analyzed was the object's position along its path inside the solar system. Relative proximity to the Sun has a direct influence on its behavior, since solar radiation increases the sublimation of volatile materials. As a body approaches or changes angle with respect to radiation, even small differences can alter the amount of material released. The physics involved required no hypotheses, only continuous observation. And astronomical measurements had already shown that along its route 3I Atlas experienced small oscillations in light emission, as usually happens with active objects. The relevant point was that the recent increase had been more intense than previous ones, which justified renewed attention. Temporal comparisons were based on magnitudes measured at different intervals to avoid premature conclusions. By analyzing long series, it is possible to check whether the brightness increase corresponds to a sustained trend or a one-off phenomenon. What had been observed so far showed that the change had not been an isolated pulse but part of a period of greater activity. Nevertheless, the analysis had to continue rigorously, because a larger data set allows evaluation of whether the variation stabilizes, increases, decreases, or fluctuates. Each of those behaviors has a documented scientific explanation, but it can only be determined with constant observation. Specialists also reviewed available spectral quality, although high-resolution spectroscopy data were not available for all observations. Some readings did allow comparison of relative intensity in certain light ranges. If emission increased proportionally in specific regions of the spectrum, it could indicate the presence of certain volatile compounds being released. It was not enough to define detailed composition, but it did reinforce the idea of surface activity. Those limited readings agreed with the general trend. Reflected and scattered light was greater than previously recorded. One of the analysis points was to determine whether the variation fell within the expected range for objects passing through inner regions of the solar system. Scientific literature shows that brightness increases can occur for various physical reasons, from intensified sublimation to articulated material release. The difference in this case was the speed of the change. And that did not mean anything extraordinary, simply a behavior that had to be documented precisely. The speed with which brightness had increased was a measurable fact, not a subjective interpretation. And it was precisely that speed that led specialists to examine each measurement in greater detail. Finally, as new observations were integrated into the data set, the light curve began to take on a clearer shape. Even without definitive conclusions, the record showed that the brightness increase had occurred and was consistent. There was no need to link that behavior to any hypothetical event, because the physical mechanisms observed in active bodies were sufficient to explain the variation. From there, the priority became to continue measuring, comparing, and documenting every change in order to build a continuous record of the phenomenon. Once it was established that the brightness increase was real and not the product of instrumental failure, attention turned to previous records that described the photometric behavior of 3I Atlas. During its recent trajectory, the models developed for active objects allow approximate light curves to be predicted based on thermal variations, distance from the Sun, nucleus orientation, and estimated amount of material available for sublimation. These projections are not exact, but they provide a solid reference for detecting significant deviations. In this case, the observed values did not fully match what was expected for that point in its path, which required careful technical review to understand why the data were deviating from the anticipated line. The analysis began by reviewing measurements taken weeks earlier, when the brightness curve showed a relatively stable pattern. That stability is normal when the object maintains a constant rate of material release, but as time passed, small oscillations began to appear, also common in moderately active bodies. Those variations were not worrying in themselves. However, they provided important context for interpreting the recent jump. The key was to compare the slope of the curve before and after the increase, and what was clearly visible was that the rate of change had increased more strongly than in earlier phases. To understand the difference between models and data, researchers first considered the effect of solar radiation. Interaction with sunlight generates enough energy to sublimate volatile compounds on the object's surface, causing particle ejection that subsequently reflects more light. The models estimate the intensity of that sublimation according to proximity to the sun, but actual behavior can vary depending on exact composition and physical state of the material. If a surface region contains more volatile deposits or cracks that allow sudden gas release, activity can increase over a short interval, altering apparent luminosity. That type of variation is known in scientific literature, but what drew attention was the discrepancy between the measured intensity and the predicted intensity. Earlier records suggested that at that specific moment the object should have maintained brightness within a narrow margin. Instead, the curve showed a more marked increase. This did not contradict any physical principle, but it did indicate that initial projections needed to be updated to reflect the observed real behavior. And it is precisely in that adjustment process that much of observational science resides, confronting models with concrete data and modifying estimates so they better represent what is actually happening. Another aspect analyzed was coma stability. Light distribution around the nucleus allows inference of how much matter is being released. If brightness increases proportionally throughout the entire coma extent, it means there is generalized material release. But if the increase is concentrated closer to the nucleus, it indicates activity may be emerging from a localized region. Available images showed that brightness had intensified both in the apparent nucleus and in the surrounding region, suggesting a global increase in activity rather than a one-off event. That behavior did not invalidate any physical model but did require review of how parameters were being applied. During the analysis, possible sources of environmental interference were also reviewed. Although consistency among observatories practically ruled out measurement errors, it was still necessary to evaluate atmospheric conditions at each site. Changes in humidity, temperature, or turbulence can affect detection quality, but in this case the original records included sufficient controls to confirm that conditions were adequate. Moreover, data from different latitudes further reinforced measurement reliability, since each team worked under completely different atmospheric contexts. Agreement among them eliminated any possibility that the increase was an external distortion. Other reviewed aspects included sensor calibration. CCD and CMOS detectors used for photometry require periodic adjustments to maintain accuracy, but each observation session incorporates calibration files that correct for thermal variations, electronic noise, and optical effects. Specialists recalculated every observation with independent calibrations to ensure the brightness increase was not the product of some instrumental deviation, yet even with repeated calibrations the values remained coherent, confirming that the observed increase had a physical rather than technical origin. An essential part of the work consisted of comparing the current variation rate with earlier phases. This allows determination of whether the change is part of a repetitive pattern or represents a temporary acceleration. The data showed that although 3I Atlas had previously exhibited oscillations, none had reached the slope observed now. Nevertheless, the behavior remained within the possible range. For an active body exposed to intense thermal effects, there was no indication that the phenomenon lay outside what has been documented in other objects with similar characteristics. It was simply a record that required full understanding. As the review progressed, an important point emerged. Initial models had been built from limited data, and as happens with any object that does not follow a known periodic orbit, projections are always subject to change as new measurements are incorporated. Researchers emphasized that the deviation between model and reality did not mean the calculations were wrong, but that the object's actual behavior was providing additional information that had not been visible before. In science, that does not represent a failure but an increase in the precision of understanding. Another observed point was variation in the nucleus-coma ratio. During periods of greater activity, the boundary between the two becomes less defined due to increased particles scattering light. Recent images showed exactly that characteristic. A smoother transition between central brightness and brightness in the surrounding region. That pattern matches increased material release, a well-documented physical process. Although it did not by itself explain the entire discrepancy between models and observations, it did reinforce the idea that activity was more intense than in previous days. The final part of the analysis focused on the temporal evolution of the curve. As more observations were added, the graph showed that the increase had occurred over a relatively short period and with a steeper slope than projected. This led to the conclusion that older data no longer represented a sufficient reference. With each new measurement, the theoretical line had to be slightly adjusted to reflect what was really happening. And that continuous adjustment process is precisely what allows science to advance based on direct observation rather than static estimates. When the most recent data were finally integrated, it became clear that the observed behavior corresponded to a phase of intensified real and quantifiable activity. It was not an inexplicable anomaly or a phenomenon outside what has been documented in active objects, but a natural update within the monitoring process. The brightness increase did not invalidate the models. It forced them to adapt in order to include more accurate information about the object's interaction with its immediate environment. And it is precisely that interaction that would continue to be evaluated in detail in subsequent stages of the analysis. After the detailed review of values that did not match initial projections, the next natural step was to examine how brightness changes were actually being measured in 3i Atlas. To interpret any variation accurately, it was essential to understand every stage of the measurement process, from light capture in detectors to comparison between consecutive nights. Astronomical photometry is not merely recording an image. It is a set of techniques that require stability, rigorous calibration, and consistency among instruments. In the case of 3i Atlas, the data came from a combination of professional telescopes and observation stations equipped with high-sensitivity sensors, all capable of recording magnitudes with very small error margins. The work began with how light was captured. Telescopes use specific filters that allow measurement of luminous intensity in defined spectral ranges, generally in optical bands such as the R or G band, depending on the equipment. By observing the same object with different filters, astronomers can evaluate variations in light scattering and determine whether certain ranges intensify more than others. In the case of 3i Atlas, several data sets showed that the brightness increase was consistent regardless of the filter used, reinforcing the idea of a real increase in reflected light rather than a fluctuation in a specific band. Each captured image underwent a calibration process that included corrections using dark frames, bias, and flat fields. These steps remove sensor thermal noise, adjust electronic response, and compensate for optical field irregularities. Only when all adjustments were applied was the image considered suitable for measurements. That technical rigor allowed comparison of data from different nights without the risk of an artificial variation being interpreted as a real change in the object's luminosity. Once images were calibrated, aperture measurements were performed. This means selecting a circle around the object to calculate total light captured within that radius. If the object is more active and releases more particles, light scatters further and brightness in large apertures increases proportionally. When small, medium, and large apertures of 3i Atlas were compared, a notable increase was found in all of them, indicating that both the apparent nucleus and the coma had increased reflectivity. That behavior ruled out the possibility that the increase was concentrated only in a central region, showing that surface activity was affecting the entire diffuse structure around the nucleus. Another central point was to evaluate sky stability during each observation. Photometry requires consistent atmospheric conditions because turbulence can distort captured light flux. Each record included information on seeing, transparency, and temperature variations. The data showed that the nights when the brightness increase was detected had conditions suitable for precise measurements. That information strengthened detection reliability, since a real change should not be attributed to a particularly turbulent or cloudy night. Furthermore, each measurement was compared with reference stars present in the same field of view. Those stars have well-documented magnitudes and are used as calibration points to verify whether the object's brightness is being measured accurately. If the magnitude of the standard stars remained stable, it meant the object measurement was also reliable. In the observations of 3i Atlas, the standard stars showed constancy within the acceptable margin, indicating that the detected increase was not a calibration error but a real phenomenon of the object itself. The most delicate part of the analysis involved reviewing temporal consistency of the measurements. For this, Specialists compared light curves built from long series of observations, some with minute intervals and others with day intervals. This multi-temporal approach allows identification of rapid fluctuations and sustained changes. For 3I Atlas, it was observed that the recent increase was not just an isolated pulse detected in a single session but a pattern that persisted across several records. This reinforced the interpretation that it was a period of intensified activity rather than a one-off effect caused by external factors. When examining images in greater detail, astronomers also looked for morphological changes in the coma. Although the resolution of many telescopes does not allow extremely fine details, it is possible to evaluate general expansion of the material halo around the nucleus. In comparisons made before and after the increase, the coma appeared slightly more extended, consistent with greater release of fine particles that reflect sunlight. That expansion was not dramatic, but it was enough to influence measurements and contribute to the recorded brightness increase. Another evaluated aspect was the phase angle, which indicates how sunlight strikes the object and how that light is reflected toward observers on Earth. Changes in that angle can alter apparent luminosity, but recent variations in 3I Atlas were not large enough to explain the observed increase. This allowed ruling out the possibility that the increase was due solely to change in illumination geometry, reinforcing that a physical component was involved. Acquisition of data from different observatories allowed specialists to evaluate consistency among instruments with different optical characteristics. Larger diameter telescopes capture more light and can detect subtle variations with less uncertainty, while smaller telescopes provide observation frequency, offering more continuous records. In the case of 3I Atlas, both types of instruments confirmed the same pattern. The magnitude had changed and the change was consistent. As astronomers compiled more data, it became evident that the measurements were describing a phenomenon that fit patterns observed in active bodies subjected to temperature increases and surface structural variations. The brightness increase did not arise from a sudden inexplicable event but from a gradual physical process that reached a higher intensity point than recorded days earlier. That interpretation allowed continued progress in the analysis without abandoning the solid scientific basis that characterizes the study of active objects. In summary, the way brightness was being measured revealed real, verifiable behavior backed by multiple instruments. Every stage of the process, capture, calibration, photometry, repetition, and comparison among observatories, pointed to the same result. 3I Atlas was brighter. And that rigorously measured fact would serve as the foundation for subsequent analyses that would continue exploring its behavior inside the solar system. With the values confirmed and photometric measurements verified, the analysis began to focus on the surface activity of 3I Atlas, an essential aspect for understanding any luminous variation in an active object. Activity does not refer to extraordinary phenomena but to well-documented physical processes that occur when a body composed of volatile materials is exposed to intense solar radiation. As an object approaches the sun or passes through regions where incident energy increases, certain compounds begin to sublimate, passing directly from solid to gaseous state. That process generates ejection of microscopic particles that spread around the nucleus and form the coma, a diffuse region that reflects sunlight with efficiency depending on the density of released material. In recent observations, the behavior of 3I Atlas showed signals consistent with an intensified activity phase. Although the object's morphology could not be observed in great detail by ground-based telescopes, the captured light distribution indicated that particle release was increasing. This type of increase is far from unexpected in active objects, but what made 3I Atlas draw so much attention was the speed with which that change had manifested. Newly released particles, as they spread into the coma, increased the object's reflectivity, which translates directly into a brighter magnitude. That effect is strong enough to be recorded even by smaller telescopes, explaining the consistency among observatories. To better understand the internal dynamics of that activity, specialists reviewed temporal comparisons of the coma. This analysis consists of evaluating how light distribution around the nucleus changes as the object releases material. A more extended coma tends to scatter light in a characteristic way, while a denser coma produces more concentrated brightness in certain regions. Recent records of 3I Atlas showed a combination of both effects, indicating that new particles were distributing and contributing to the overall luminosity increase. This pattern matches behavior observed in various active bodies without need to invoke unknown mechanisms. It is a natural process resulting from interaction between volatile materials and solar radiation. Another aspect that became relevant was the luminous texture of the immediate environment around the nucleus. Although it is not possible to directly observe the solid nucleus with conventional optical instruments due to coma scattering, the relative intensity of the inner region can be inferred. An increase in that zone suggests sublimation occurring more strongly in regions with deposits more sensitive to heat. That interpretation is consistent with models explaining why certain objects show sudden brightness increases. When a section of surface material heats sufficiently, even a small temperature change can trigger faster particle release. Observed data from 3I Atlas showed exactly that type of internal increase detected without need for high-resolution observations. The object's thermal behavior was also examined based on its position in the solar system. Although there was no extreme variation in sun distance to justify a massive activity increase, small differences in incidence angle can influence sublimation. The sun does not illuminate all objects the same way at every point in their trajectory. As the object rotates and advances, different surfaces orient toward radiation, generating natural fluctuations in material release rate. The position of 3I Atlas during the latest observations suggested it may have reached a more favorable angle for sublimation in certain sectors, explaining part of the increase without considering any abrupt process. Coma expansion was also analyzed from a density perspective. While expansion indicates material release, density determines how much light each section of the cloud can reflect. In photometric records, a slight increase in brightness uniformity was noted, something that usually occurs when the amount of fine particles increases steadily. Smaller particles have greater relative surface area, allowing them to reflect more light per unit of mass. If recent sublimation of 3I Atlas generated a significant number of such particles, it was perfectly reasonable to observe a general luminosity increase even without following the previously projected gradual pattern. Another element considered was possible release of microscopic fragments. Although no evidence suggested major fragmentation, release of slightly larger particles than common dust also affects reflectivity. Those particles behave differently from finer ones because they can remain in the inner region longer before dispersing, contributing to what is perceived as a brighter nucleus. Photometry showed patterns compatible with that presence, although precise particle size could not be determined. This type of release is frequently documented in active objects and can vary over time depending on exposed material. Likewise, interaction with solar wind was examined. Although solar wind can influence coma shape and direction of expelled material, no evidence was found that it was significantly affecting measured magnitude. In 3I Atlas records, light distribution did not show extreme asymmetry indicating strong wind effect. Still, its role could not be completely ruled out, since small alterations in material distribution can modify how sunlight scatters at different angles. Thermal evolution also became relevant. Even a slight surface temperature variation can modify sublimation rate of certain compounds. In objects with complex volatile mixtures, as believed to occur in many interstellar and cometary bodies, release of different materials can produce distinct brightness increases. Although available data for 3I Atlas did not allow determination of which compounds were sublimating at that moment, simple activity intensification was sufficient to explain greater reflectance without relying on external or hypothetical explanations. As more observations accumulated, record consistency reinforced that the brightness increase did not come from a single one-off event but from a combination of natural processes that amplified within a relatively short interval. The object was not acting outside what is expected for an active body, but it was providing new information about how its material responded to current thermal conditions. And that in itself represented a relevant scientific component, allowing adjustment of interpretation of its behavior while staying within observational evidence. In conclusion, confirmed surface activity of 3I Atlas provided a solid and scientifically consistent explanation for the recorded brightness increase. The process was coherent with known, verifiable, and repeatedly observed mechanisms in other active bodies. The interpretation required no speculation, only continuous observation and analysis. As the object continued advancing within the solar system, the data showed that its interaction with solar radiation was leaving clear and measurable traces in its luminosity, reinforcing the importance of following these changes with technical rigor. Upon entering the phase of comparison between previous days and the most recent records, specialists' attention focused on how the light curve of 3I Atlas had evolved over time. It was not just about identifying the most notable increase but understanding precisely how the slope of each segment had changed and how quickly that change had manifested. That temporal comparison is one of the most important tools for studying objects with variable activity, because it distinguishes between brief fluctuations and sustained behavior. In the case of 3I Atlas, values collected over the last few weeks showed a pattern that began relatively stable, with small typical oscillations of moderate sublimation, until deviations gradually appeared that exceeded the usual margin. The first perceptible variations had emerged gradually, as seen in many active bodies when surface temperatures rise slightly. However, the most recent values began to trace a steeper line in the light curve, indicating that material release was occurring at a higher rate than previously recorded. That acceleration was not necessarily abrupt, but it was clear enough to highlight a difference between distinct phases of the object. When comparing consecutive nights, astronomers noted that apparent magnitude showed measurable changes over relatively short intervals, reinforcing the importance of carefully analyzing temporal evolution. To understand that difference more precisely, specialists reviewed measurements captured during complete night periods. Continuous analysis within the same night eliminates the possibility that variation comes exclusively from atmospheric conditions or one-off equipment errors. What was found was notable internal stability in each individual session, indicating that the increase had not occurred as a sudden jump within a very short interval but as part of an accumulated trend observed across different nights. That consistency across sessions was essential to confirm that the increase corresponded to a physical response of the object rather than an observation artifact. When extending the comparison several days back, it became clear that 3I Atlas brightness had increased at a rate higher than projected by initial models. It was not just a value out of place but an entire segment of the curve showing stronger inclination. That characteristic was particularly evident when placing records of successive dates side by side, demonstrating that magnitude had not only changed but had done so following a coherent trend. This trend allowed ruling out the possibility that the increase had been an isolated peak, since an isolated peak would appear as an anomalous point followed by an immediate return to the previous level, something that was not happening. Another important point of temporal comparison was to review images captured in specific filters to determine whether any spectral range had shown a more pronounced increase. Although the increase was general, some records indicated that response in certain optical filters had increased slightly more than in others, possibly related to variable particle density within the coma. Still, the difference was not large enough to attribute the phenomenon to a single type of material, but rather reinforced the idea of a generalized increase in reflectivity of the particle set around the nucleus. As data from previous weeks were reviewed, researchers looked for patterns that could explain the acceleration. In many active bodies, brightness increases can be associated with variations in material release rate as the object rotates on its axis. If a particularly radiation-sensitive region enters direct exposure, that area can release more particles during a limited interval, producing a gradual increase that only becomes evident when rotation moves that region to a less illuminated zone. Although no direct observations allowed determination of 3I Atlas rotation period, brightness distribution suggested that certain zones could be responding to thermal changes more intensely than others. As the temporal comparison progressed, the balance between finer and slightly larger particles forming the coma was also reviewed. Smaller particles respond very quickly to thermal changes, while larger ones can remain near the nucleus longer before fully dispersing. In the most recent observations, light appeared to be scattered by a more abundant mixture of fine particles that increase luminosity more efficiently. That characteristic could explain why the last few days' data showed more intense variation than recorded in earlier stages, when particle proportion was likely different. Continuous follow-up allowed seeing that although there was some night-to-night variability, the overall curve had a clear direction. When placing all measurements on a timeline, a continuous transition was observed from more moderate values towards significantly higher levels. There were no signs of irregularity suggesting pattern interruption but rather sustained progression. That progression was especially important because it allowed data interpretation adjustment without resorting to abrupt conclusions. What was seen was an active object displaying a more intense activity phase, fully explainable from the physical point of view. At each stage of temporal analysis, astronomers had to ensure that observed trends were not influenced by external factors such as object elevation in the sky or moon proximity on certain nights. These factors can alter sky quality and affect reading accuracy, but records included sufficient controls to rule out such influences. Nights with less atmospheric stability were corrected or discarded, and the general trend remained intact. That statistical robustness reinforced analysis reliability. Another relevant aspect was comparison of curves generated by telescopes of different diameters. While large telescopes can detect changes with greater precision, smaller telescopes are essential for providing temporal continuity. In the case of 3i Atlas, both types of instruments agreed on the general shape of the curve. That agreement was fundamental, as it validated the observed behavior from different geographic points with very different technical characteristics. If there had been significant discrepancy, further investigation would have been required, but that was not the case. As the comparison advanced toward more recent dates, specialists began to see patterns connecting thermal activity with coma density variation and increasing uniformity in brightness scattering, suggesting the object was releasing particles more consistently. That uniformity matched behavior observed in other bodies subjected to gradual thermal increases, reinforcing the physical explanation without need to extrapolate unproven scenarios. Finally, when synthesizing all temporal observations, the conclusion was clear. The brightness increase observed in recent days represented a more intense active phase than the previous weeks, perfectly coherent with the dynamics of an object exposed to thermal changes within the solar system. The data reflected a real, sustained, and scientifically explainable variation that continued to develop as new observations were incorporated. When the sustained and verifiable brightness increase of 3i Atlas became firmly established, researchers began to analyze what that change could mean from a purely physical perspective, without speculation and without assuming extraordinary phenomena. Scientific interpretation of a luminosity increase in an active object depends on a series of mechanisms studied in numerous bodies over decades, so it was important to contextualize the phenomenon within those known processes. The brightness of an object like 3i Atlas is essentially the sum of sunlight reflected by its surface and by the material it expels, including gases and particles of different sizes. When that amount of material increases, luminosity also increases, and that basic principle guides the entire analysis. To understand what the increase meant, specialists first reviewed the overall activity level reflected in the coma. If an object steadily releases more material, coma density increases, and with it the capacity to scatter light. This does not necessarily imply internal structural change but simply a natural physical response to increased received energy. The data indicated that 3i Atlas was reflecting more light than days earlier, suggesting that interaction between its surface and solar radiation had intensified. The key was to determine whether that intensification followed a gradual pattern or represented a particularly active phase within its current trajectory. To answer that question, scientists analyzed efficiency with which the object was scattering light in different spectral ranges. Although observations focused mainly on optical bands, recorded variations suggested a generalized increase in material reflectivity, consistent with greater presence of fine particles. Those particles, when exposed to the sun, reflect light more efficiently than larger particles, which tend to absorb more energy before scattering it. That difference in optical response was key to interpreting why brightness could increase without drastic changes in overall structure. Another relevant indicator was the surface material's thermal response. Active objects usually contain volatile deposits that react to small temperature variations. Unlike surfaces composed only of rock or metal, volatiles can sublimate even with relatively modest temperature changes. The position of 3i Atlas within the solar system during recent observations suggests that incident solar energy was sufficient to intensify sublimation in certain surface sectors. There was no need to assume a sudden internal temperature increase, since prolonged exposure to radiation can accelerate already ongoing processes. That behavior is coherent with active objects and their reaction when passing through more illuminated regions. The analysis also considered the possibility that the object was releasing particles from cracks or cavities that only become active under direct illumination. In non-homogeneous nuclei, certain regions can respond disproportionately when radiation strikes at specific angles. If a previously less exposed zone begins receiving direct illumination, it can release more material without interpreting the phenomenon as unusual. This behavior has been documented many times in solar system comets and is considered one of the most likely mechanisms behind changes like the one recorded in 3i Atlas. Another crucial point evaluated was the relationship between coma density and the amount of energy the object was absorbing. As the coma becomes denser, particles can interact, reflecting and scattering sunlight in more complex ways. These processes can amplify or smooth brightness appearance depending on spatial distribution. In the case of 3i Atlas, distribution appeared to reach greater uniformity compared to days earlier, suggesting more constant particle release. A more homogeneous distribution tends to perceptibly increase luminosity because it reduces internal shadow zones and increases efficiency of light reflection toward Earth. Furthermore, specialists analyzed correlation between brightness variation and speed at which material was expelled. Although this parameter cannot be directly measured with optical observations, it can be inferred from coma shape and speed at which apparent edges change. In recent records, no distortion suggested explosive or irregular release but rather smooth expansion compatible with sustained activity increase, reinforcing that the change resulted from a continuous rather than abrupt process. Available energy to drive these processes also plays an important role. As the object continues its trajectory within the solar system, interaction with solar radiation changes according to angle, distance, and orientation of exposed material. Small variations in any of these factors can cause appreciable fluctuations in activity. Researchers noted that even without significant approach to the Sun, the object could experience conditions temporarily favoring sublimation of more sensitive volatiles. Again, the data showed no behavior outside what is physically explainable. The amount of material expelled by an active object also directly influences its apparent mass and how its luminosity evolves over time. When volatiles sublimate, part of the gas can drag particles contributing to the coma. If the material mixture includes compounds sublimating at different temperatures, the object can show more pronounced brightness increases at specific moments. Records associated with 3I Atlas suggested that the recent variation was linked to that type of behavior without signs of irregularities requiring exceptional explanations. The analysis became even more interesting when comparing luminous variations with other active objects observed in previous decades. Although 3I Atlas does not share origin with traditional solar system comets, its photometric behavior in this phase was surprisingly similar to bodies experiencing activity increases due to volatile sublimation. That similarity reinforced the classic physical interpretation and provided a solid reference framework for analyzing changes without extrapolating beyond what data allowed. Finally, the synthesis of the analysis showed that the brightness increase simply and directly meant that 3I Atlas was going through a period of greater surface activity. The records pointed to a set of physical mechanisms coherent with this type of behavior, all verified and supported by previous studies. What was happening was a natural phenomenon within the known repertoire of processes in active bodies under solar interaction. And it was precisely that observable and measurable physical process that clearly and scientifically explained the recorded luminous variation. In the most recent data, when brightness increases were firmly established and surface activity appeared to respond to known physical mechanisms, the next necessary step was to verify whether other observatories around the world had recorded similar patterns. Independent confirmation is one of the most important pillars of modern astronomy because it rules out local errors and validates phenomena not dependent on a single instrument or methodology. In the case of 3I Atlas, the scientific community had already maintained constant follow-up before the luminosity increase, and that global observation network proved crucial for understanding recorded behavior consistency. The starting point was to review measurements from professional telescopes on different continents. Each observatory has unique optical characteristics, different altitudes, specific atmospheric conditions, and variable light pollution levels. Obtaining agreement among their data provides especially robust verification. First comparisons showed that values detected by telescopes in North America matched magnitudes recorded by teams in Europe and Asia. That repeated agreement on nearby dates confirmed that the brightness increase could not be attributed to regional artifact or particular sky conditions. As more observations were reviewed, a detailed map could be drawn of records obtained almost simultaneously by different teams. The increase was detected across very different latitudes, from equatorial regions to stations in colder northern hemisphere zones. Telescopes operating under dry and stable skies, such as those in certain desert regions, recorded values practically identical to those from observatories in more humid environments, always within accepted photometric error margins. That data convergence reinforced phenomenon reliability. Records from observatories equipped with special filters also played a key role. Some telescopes used narrow filters designed to capture specific compound emissions, while others used broadband filters measured overall brightness. When both techniques show similar trends, it means the observed behavior is strong enough to appear in both integrated and selective measurements. Observations of 3I Atlas confirmed that coincidence. The brightness increase was evident in both filter types, demonstrating that luminous intensification affected the entire particle set forming the coma. While that evidence consolidated, some centers began more precise comparisons between locally generated light curves and those published by other teams. The process involved overlaying graphs taken on nearly identical dates and analyzing differences at each point. This technique identifies whether one observatory's results deviate from the general trend, possibly indicating instrumental or atmospheric error. In performed overlays, 3I Atlas curves showed remarkable alignment, demonstrating that instruments were recording the same phenomenon from completely different perspectives. In addition to professional observatories, networks of experienced amateur astronomers using advanced personal equipment also contributed. Although those instruments usually have smaller apertures, their value lies in observation frequency. That temporal density filled gaps between records from larger telescopes, creating a continuous data line difficult to achieve solely with professional facilities. When measurements from these independent observers were placed alongside those from large aperture teams, the agreement was remarkable, further reinforcing that the brightness increase was real and not methodological illusion. While light curves were verified, another fundamental aspect was to examine consistency in coma morphology. Although smaller telescopes could not capture fine details, many could detect changes in overall luminous halo extent. Images taken from different world regions showed the coma appeared slightly wider than days before, a pattern consistent with more active particle release. When those images were placed side by side, not only the same behavior was observed but also the same development rate of the expansion. That morphological agreement among independent records added another layer of verification. Some observatories with high-sensitivity cameras captured images with enough resolution to detect small differences in light distribution. Those images, sent to shared research databases, showed luminous texture consistent with moderate activity increase. Radial brightness profiles, showing how intensity decreases from nucleus to coma, displayed the same general shape across multiple stations. This was especially important because if a brightness increase were due to instrumental error, radial profiles would not coincide. However, in 3I Atlas they matched with remarkable precision. As analysis progressed, historical records of luminous behavior in other active objects were also reviewed for context. Although 3I Atlas does not share origin or trajectory with periodic solar system bodies, brightness increase patterns recorded by observatories in different regions were very similar to those documented in objects that experienced similar activity phases. That parallelism allowed reinforcement of the physical interpretation and showed that the recent variation fell within known and measured behavior range in active bodies exposed to solar radiation. Most importantly, even with completely different equipment, the brightness increase trend remained well defined. Large, medium, and small telescopes agreed on relative magnitude values. That convergence almost completely reduced the possibility of data being influenced by local errors. In fact, when researchers combined all observations into a single global graph, the resulting light curve showed surprising continuity, revealing the same ascending behavior identified in individual records. With all those elements together, the evidence was conclusive. The brightness increase of 3I Atlas had been verified by multiple observatories from different planetary regions using different techniques and equipment of diverse capabilities. Agreement among observations demonstrated that the variation was real, measurable, and physically coherent with known surface activity mechanisms. That independent verification greatly strengthened scientific interpretation and eliminated any reasonable doubt about its authentic nature. With independent verification confirming the brightness increase and establishing that the phenomenon was real, the scientific community's focus turned to specific signals that could be monitored to understand 3I Atlas' immediate evolution. Although brightness is one of the most direct measures for evaluating activity, other indicators allow analysis of how the object interacts with solar radiation and what type of material it is releasing at each phase. The key at this stage was not to anticipate future behavior but to observe with precision every present variation and document its evolution as faithfully as possible. Observatories began concentrating attention on objectively measurable elements: coma extent, light scattering consistency, magnitude stability over short intervals, and uniformity in luminous structure around the nucleus. One of the first monitored signals was change in angular brightness distribution. When surface activity increases, the coma can show denser regions or differently scattering zones. If material is released at higher speed, distribution pattern tends to become more uniform, as newly ejected particles spread without forming very marked anisotropic structures. In recent 3I Atlas observations, Light showed no signs of irregular concentrations but rather homogeneous scattering corresponding to continuous fine particle release. That uniformity was consistent with intensified activity interpretation because it indicated relatively even material expulsion in different directions. Monitoring internal coma structure also proved essential. Although optical resolution does not allow direct observation of the solid nucleus, intensity change near the apparent center can be analyzed, providing valuable information on sublimation speed and material density in that region. In reviewed images, light near the center showed slightly greater concentration than weeks earlier, suggesting sublimation occurring at increased rate. That concentration was neither extreme nor indicative of instability but represented a natural material response to changing thermal conditions. Another observed signal was magnitude stability over very short periods. When an object shows chaotic activity, its brightness can fluctuate perceptibly even during a single night. However, in 3I Atlas records brightness remained stable within minute and hour intervals, indicating that although intensified, activity was neither irregular nor episodic. That temporal stability was an important indicator because it distinguished between abrupt event and continuous process. Astronomers continued monitoring that stability to determine whether the trend would persist in subsequent days, but records to that point showed behavior coherent with a sustained activity phase. The way light decreased from nucleus to coma edge also provided relevant information. That decrease follows well-documented patterns in active objects and can change depending on particle density and average size of released fragments. When comparing radial brightness profiles from different dates, a slight slope change was found, indicating increasing fine particle density. That increase in small particles is consistent with surface activity increase, as faster sublimating volatiles usually release very fine grains that efficiently scatter light. Spectral monitoring, though limited, also offered important clues. Although high-resolution spectra were not sufficient to precisely determine expelled material composition, some records allowed analysis of relative intensity in certain optical bands. In those data, a slight intensity increase in certain spectral regions was observed, possibly indicating active volatile compounds contributing to light scattering. That signal was neither intense nor dominant, but its increase accompanied the general photometric trend, reinforcing greater activity interpretation. Another monitored element was the relationship between apparent coma size and light diffusion at its edges. When an object activates new sublimation regions, the coma can expand more evidently. No dramatic expansion was recorded in 3I Atlas, but moderate and stable growth accompanied overall luminosity increase. Astronomers verified this by comparing successive images and calculating visible extent of the diffuse region. Detected growth matched typical pattern of increasing activity where coma widens as fine grains disperse. Solar wind was also monitored, not because extreme coma distortion signals existed but because small material orientation changes can influence light scattering toward Earth. Although solar wind showed no severe effects in recent observations, slight variation at outer coma edge was recorded, possibly related to solar particle flow interaction with newly expelled particles. That effect does not significantly alter apparent magnitude but helps understand material dynamics around the object. The apparent trajectory of 3I Atlas was also carefully monitored. Although its sky position does not directly influence physical activity, it affects how light reaches Earth observers. Nightly altitude changes can slightly alter measurement quality, but records included sufficient corrective data to ensure observed variations did not originate from those factors. Still, trajectory allowed more precise calculation of solar energy received at each stage, aiding activity interpretation. Internal coma stability measured through light scattering patterns was another crucial point. If the object were undergoing structural collapse or destructive process, the coma would show irregular patterns, severe asymmetries, or sudden brightness variations. None of those behaviors was present in 3I Atlas. On the contrary, the diffuse structure remained stable, indicating no evidence of violent or unexpected processes. Morphological stability was a key indicator that observed behavior remained consistent with moderately intensified but natural active phase. In summary, signals monitored by different teams indicated that 3I Atlas was in a stronger activity state than weeks earlier but completely coherent with physical processes affecting active objects within the solar system. Brightness evolution, coma extent and structure, temporal stability, and optical scattering coincided to form a clear scientific picture. The object was releasing material more intensely, thus causing the luminosity increase detected by multiple observatories. With activity signals established and brightness increase consistency confirmed by multiple teams, one of the most important aspects for correctly interpreting 3I Atlas behavior was to precisely determine where the object was located within the solar system. At the time of the most recent observations, an active object's position is essential because it determines how much solar energy it receives, which surface regions are most intensely exposed, and how interaction with solar wind and radiation affects particle release. Understanding spatial context in which the brightness increase occurred was fundamental for analyzing the phenomenon without additional assumptions. During the latest measurements, 3I Atlas continued its path through a region where solar radiation has sufficient influence to cause sublimation in volatile materials. Although not undergoing extreme solar approach, its distance was small enough to maintain moderate activity level. That energetic condition, combined with its orientation relative to the Sun, facilitated physical processes that could explain recorded luminosity increases. The object's trajectory, still within the solar system and regularly monitored, allowed astronomers to precisely calculate its position and angular velocity at every moment, indispensable for correlating activity with illumination conditions. One of the most relevant elements for interpreting its location was phase geometry, indicating the angle between Sun, object, and Earth. That angle directly influences amount of light reaching observers. When the angle is small, the object can appear brighter because reflected light arrives more directly. However, in recent observations, phase angle variation was not large enough to alone justify the recorded increase, indicating that the object's physical activity played a much more important role than illumination geometry, reinforcing what photometric measurements had already shown. Still, phase geometry helped understand how light scattered by the coma behaved. From the observer's viewpoint, if the object moves to a region where illumination favors scattering toward Earth, expelled material visibility increases. This effect does not create artificial brightness increase but can amplify perception of real activity. In 3I Atlas case, the sky position during analyzed dates favored clear and stable scattering, allowing brightness variations to be recorded with greater precision. Orbital analysis also allowed evaluation of how the object's relative velocity affected apparent coma size. As a body moves through the solar system, its motion can cause slight optical effects altering particle distribution around the nucleus. However, those effects did not significantly alter observed magnitude, since coma-composing particles move at velocities dominated by sublimation processes rather than orbital motion. What was relevant was that orbital position allowed estimation of surface-received energy at each moment. Another important aspect related to its location was distance between 3I Atlas and Earth. Over recent weeks, an object can appear brighter simply by being closer to observers, but orbital measurements showed distance had not experienced significant enough change to explain recent luminosity increase. This was a key point because it completely ruled out variation being due to geometric proximity effect. Confirmation was clear. Surface activity was the main responsible for brightness increase. Orbital information also showed how the object's orientation relative to the Sun had changed. As it advances, different regions become exposed to variable radiation levels. If a previously partially shaded area begins receiving direct illumination, it can release volatiles faster, producing perceptible activity increase. Although no images could directly show which nucleus regions were active, orbital position allowed inference that certain zones may have entered greater exposure phase. This inference was not speculation but interpretation based on well-documented solar illumination-sublimation relationship. In addition to position relative to Sun and Earth, 3I Atlas location had implications for solar wind interaction with its coma. Solar wind does not act uniformly across the solar system. Its intensity varies with heliographic latitude and solar magnetic field conditions. During analyzed dates, the object was in a region where solar wind had enough energy to influence fine particle orientation but not enough to cause extreme coma-shaped distortion. Still, that interaction could contribute small material distribution adjustments, reflected in certain observed light scattering patterns. Orbital position also allowed more precise calculation of total solar energy incident on the object's surface. When energy increases even slightly, volatile materials can sublimate quickly. That is why active objects can show significant luminosity changes even without being at closest solar point. The relevant point was that 3I Atlas' current location provided an energetic environment favoring active behavior while remaining coherent with well-established physical mechanisms in cometary astronomy. Correlation between position and activity was also confirmed by comparison with historical data of other objects in similar trajectories. Although 3I Atlas is an interstellar visitor and does not share exact properties with solar-bound comets, its photometric behavior in this phase surprisingly matched that of bodies passing through regions of gradually increasing solar radiation. That coincidence reinforced physical interpretation and showed no need to resort to external or extraordinary explanations. Finally, precise location of 3I Atlas within the solar system allowed understanding why recorded activity was consistent and sustained. Its distance, orientation, solar exposure, and geometric relationship with Earth perfectly fit a scenario where volatile sublimation could intensify due to natural and measurable causes. The object continued to be constantly monitored because its position kept it at a key point for clear photometric records, allowing even subtle variations to be detected accurately. In summary, 3I Atlas' position in the solar system during the brightness increase provided a clear physical context that helped interpret all observed data. The object was in a region where solar energy was sufficient to drive more intense activity without requiring extreme conditions. That location, combined with measurement stability, explained why luminosity had increased so consistently in recent records. With 3I Atlas' position clearly established and brightness increase confirmed by multiple observatories, researchers' attention focused on documenting what could be observed from that point onward, without anticipating conclusions or projecting hypotheses beyond available data. At this phase, priority was not to predict future scenarios but to record with maximum fidelity how object activity evolved and which signals remained measurable as it continued its trajectory within the solar system. Observational science depends on continuity and precision, and 3I Atlas offered exactly that, an active, real, and constantly developing phenomenon capable of providing valuable information with each new photometric session. One of the main focuses was to maintain continuous monitoring of its brightness. Since luminosity had shown a sustained upward trend, it was essential to continue evaluating whether that trend slope remained stable or experienced additional variations over time. Although the recorded increase had already been significant, data showed the object's magnitude remained accessible to moderate-sized telescopes, allowing a wide network of observers to contribute constant information. That contribution was especially important because it provided detailed temporal framework, enabling correlation of small changes with object rotation or new solar illumination variations. Another essential point was to observe coma evolution. If surface activity continued intensifying, it was reasonable to expect continued subtle changes in visible coma extent. It was not about anticipating major transformations but registering how expelled material density could fluctuate over hours or days. Images obtained in later sessions showed a stable coma slightly brighter than previous stages, suggesting sublimation rate continued providing enough material to maintain diffuse appearance. Although changes were moderate, their detailed record allowed construction of a coherent timeline of object evolution. As more data accumulated, specialists continued evaluating magnitude stability over short intervals. This technique detects any irregularity possibly indicating sudden sublimation changes. However, records obtained after initial increase showed notable stability within each night session, reinforcing interpretation that activity was sustained rather than episodic. That stability is common in bodies experiencing moderate activity phases, matching observed physical behavior. Each new measurement added consistency to scientific interpretation without deviating from verifiable limits. Spectral analysis, though limited by high-resolution instrument availability, remained valuable for identifying general trends. Some relative intensity variations in certain optical bands could suggest changes in fine particle proportion within coma. Most recent observations showed slight luminosity increase in ranges associated with efficient fine-grained scattering, a signal coherent with recorded photometric evolution. Those data did not allow specific composition conclusions but strengthened idea that activity persisted at elevated level. The trajectory of 3I Atlas also continued to be monitored, not because orbital displacement presented risks or irregularities but because it allowed precise determination of received solar energy. During dates following initial increase, the object remained in a region where radiation could continue driving sublimation processes. Although distance to Sun experienced no drastic changes in that interval, small orientation variations could generate differences in certain surface region activity. That type of gradual fluctuation is normal in active body behavior, confirmed by observations without complex theoretical interpretations. Interaction between the object and solar wind continued to be monitored. Although previous records showed no extreme coma distortion signals, small expelled material orientation adjustments could indicate how newly released particles responded to solar particle flow. This interaction does not significantly alter object magnitude but provides important information on emitted material dynamics. Images taken after brightness increase showed slight variations at outer coma edge, behavior coherent with moderate solar wind action on active bodies. In addition to photometric and spectral observations, researchers paid attention to object morphological stability. In cases of extreme processes or internal structural instability, coma can show marked irregularities, pronounced asymmetries, or sudden brightness variations. Nothing like that was identified in 3I Atlas. On the contrary, diffuse structure remained stable, indicating no evidence of violent or unexpected processes. Morphological stability was a key indicator that observed behavior remained consistent with moderately intensified natural active phase. Continuous monitoring also allowed evaluation of whether brightness increase rate was stabilizing. Although initial increase had been notable, subsequent observations showed elevated luminosity level persisted without abrupt fluctuations. This could indicate the object had reached temporary equilibrium between received solar energy and material sublimation rate, common in active bodies passing through regions of relatively constant temperature for brief periods. Measurements showed stable and clear signal, evidencing activity maintained at elevated but coherent level. As records accumulated, researchers focused efforts on comparing most recent data with those obtained in the phase before brightness increase. This allowed precise evaluation of current behavior duration and consistency. Comparison showed activity level was higher than weeks earlier but remained absolutely compatible with known physical processes. No instability signals or indications suggesting behavior outside expected range for active object under this radiation level were detected. In summary, what was observed from that point was natural continuation of an already confirmed phenomenon. 3I Atlas continued displaying moderately intensified activity, fully explainable by documented physical mechanisms, requiring no extraordinary interpretation. Each new measurement brought greater clarity to object behavior, allowing understanding of how its interaction with solar radiation evolved and what coma dynamics were during this period. Science advanced through concrete, verifiable, and systematic data, and 3I Atlas continued providing exactly that type of information,